Welcome back to Calculus 2. Today we're going to look at series instead of sequences. There is not much of a difference in language when you're talking about these. Often people mean the same thing when they say them. When they say sequences or series just in normal English. But in mathematics there is a distinct difference between the two. So an infinite series is the sum of an infinite sequence. So we have some sequence a sub n has, an infinite number of terms. This is a sequence. The sum of, the sequence is each term. The first term is a1, the second term is a2. But the sum of all of them, like I'm adding them here, that is the series of those terms. So a sequence is just the terms, If you're writing a sequence, you're writing each term separated by a comma. But a series is a sum. So instead of separating by commas, you're separating by addition signs because you're adding them all together. This sequence, defined by S1 is the first term, S2 is the sum of the first two terms, S3 is the sum of the first three terms. Each one of these S's is called a partial sum. So the first partial sum only has the first term. The second partial sum has the first two terms. The third partial sum has the first three terms. And the nth partial sum is the sum of the first n terms. Here's a nice way of saying it just using sigma notation. That is called the sequence. This S1, S2, S3, S4, S5, and so on is called the sequence of partial sums of the series, k equal 1 to ak. And S sub n is called the nth partial sum, as I said. Now, this is actually what determines the convergence or divergence of a series. Because some series will basically just go to infinity because you're adding an infinite number of terms, and you might think they all go to infinity, but if you think about something like the sum from k equal 1 up to n, infinity, of 1 over 2 to the n, right? Well, that's 1/2 plus 1/4 plus 1/8 plus 1/16. And you can tell what's happening to this as you go, because you start at 1/2. Here's 1 over here. You add 1/4. You add 1/8. You add 1/16. You add 1/32. It keeps halving the distance towards 1, but it does that infinitely. So as it goes through its sum, it's getting closer and closer to 1. So this actually, we would call the sum of this series is 1, or it converges to 1. Not all series will do that. I mean, if you take a very simple case, k equal 1 up to infinity of n, 1 plus 2 plus 3 plus 4 plus 5, that just goes to infinity. The sequence of partial sums does as well. So if the sequence of partial sums, since that is a sequence, converges to a limit, we say the series converges, and the sum of the series is L, that limit. If the sequence of partial sums doesn't converge, we say the series diverges. Even though we're saying the series converges or diverges, the infinite series, what actually determines the convergence or divergence is not the series itself, but the sequence of partial sums. The convergence of the infinite addition of all the a's is dependent upon what the sequence of partial sums does. It's a small distinction, but it's worth making because it's very easy to forget. I'll have a slide that actually reminds us of it at the end here. So yeah, don't confuse a sequence with a series. Don't forget that if a series converges or diverges based on its sequence of partial sums. Lastly, we're going to talk a little bit about geometric series. Geometric series are just series of the form where you have a constant times a common ratio, and the ratio just increases with every term. So for example, sum n equal 1 to infinity of, let's say, 3 to the n. Okay? 3 to the n minus 1. You just have a 1 times the first thing. The first term is 1. The second term is 1 times 3. The second term is 1 times 3 squared. The third term is 1 times 3 to the third, etc., etc., etc. I think I skipped a term there. Be 1 plus 1 times 3 plus... There's no need for me to multiply by the 1. 3 squared plus 3 cubed plus ... The nice thing about geometric series is that they are very easy to determine whether they converge or diverge. You only have to note what A is and what R is. R is called the common ratio because it just is the ratio of one term to the next. You just multiply by R to get to the next term. You divide by R to get to the previous term. Here's the rules. But let's see where they come from. So, if R equals 1, it's the simplest case. We're summing up K equal 1 up to infinity of, I think they used n, so I'll use n, of A times R to the n minus 1. So, if R equals 1, we have the sum A times 1 to the n minus 1. So n minus 1, it doesn't matter. This is just n equal 1 up to infinity. So this is just the sum n equal 1 up to infinity of A. So let's look at the sequence of partial sums. S sub 1 is of course A. S sub 2 is A plus A. S sub 3, A plus A plus A. That's 2A, 3A, and I think you can probably jump to what S sub n is going to be just based on that. S sub 4 will be 4A, so S sub n equals NA. So what's the limit as n goes to infinity of S sub n? Well, that's the limit as n goes to infinity of NA, which equals whatever A is, as long as A isn't 0, then this is going to be infinity, or negative infinity, but regardless, diverges. So if R equals 1, diverges. So that takes 1 out. Let's look at if R is less than 1. Well, S sub n, we know, is A plus AR plus AR squared plus ... plus AR n minus 1 plus, AR n minus 2 plus AR n minus 1. Because remember, our sum is AR to the n minus 1. K equal 1 up to n. Alright, well, so that would be K into infinity. What's the K equal 1? K minus 1. So S sub n would be that. Now let's look at what R times S sub n will be. Just bear with me. So that would be AR plus AR squared plus AR cubed plus ... AR n minus 1 plus AR. Basically, increase the power of R in every term. Now let's subtract those. So let's look at S sub n minus R times S sub n. Turns out it's not even less than 1. Let's just... I forgot, this proof actually is proof for anything but 1, so it also allows for greater than 1. Let's see. AR minus AR, AR squared, AR cubes are going to go away. The only thing that's still going to be there is A, and then this AR. A minus AR. S sub n times 1 minus R equals a times 1 minus r to the n whoops. So S sub n equals a times 1 minus r to the n over 1 minus r. Now, since this is true whenever r is not equal 1, if we look at the limit as n goes to infinity of S sub n, limit as n goes to infinity of 1 minus r to the n over 1 minus r. Let's see, of a 1 minus r to the n 1 minus r. If r is less than 1 in absolute value, r to the n will go to 0. Because, like 1/2 to the n, as n goes to infinity, will get smaller and smaller. 1/2, 1/4, 1/8, 1/16, etc. So in that case, this will go to a over 1 minus r. If absolute value of r is greater than 1, then r to the n will go to infinity. And this diverges. And that's the proof. That's where we get our different consequences looking at down here. If the absolute value of the common ratio is less than 1, geometric series converges, and we know its sum. If the absolute value of r is greater than or equal 1, series diverges. So if it's equal 1, diverges, greater than 1, diverges. Let's look at some exercises. First off, we're just going to start by finding a formula for the nth partial sum. This is an important skill to have, as it will help you in some cases determine convergence or divergence, because if you can find a formula for the sequence of partial sums, generally we're pretty good at determining whether a sequence converges or not. A series is much harder. So let's see here. You can see the 9 in every term, so you can just factor that out. 9, and then you can see that's 1 over 100, 1 over 100 squared, 1 over 100 cubed. You can tell then that's a geometric sequence, because each term is just getting booted up a power. So this is the sum. Notice I'm just coming up with a formula for the series yet. I haven't talked about what the sequence of partial sums is. So this is the sum of 9 times 1 over 100 to the n, looks like. So just so I have the same formula, I'm going to actually say n equals 0 to infinity. Oh, actually, the first one has a 1/100th in it. This is actually 1 to infinity. I'm going to make it fit. This will be, our standard formula for geometric series has this note, n equal 1 to infinity of a r to the n minus 1. So just so it matches up, I'm going to factor out a 100 from that. That'll be 9 over 100 to the 1 over 100 to the n minus 1. Then it will match up to what we were doing. Okay, now we can say this. A is now 9 over 100, so 9 over 100 minus 9 over 100 times 1/100th to the n. Okay. So, yeah, it actually came out pretty much what we expected to. If you factor out the 9 over 100, you get a 1 minus 1 over 100 to the n. So that's the formula for the nth partial sum. The series sum, we can just use our formula for the sum of a geometric series, a over 1 minus r, since clearly 1/100th is less than 1 in absolute value. So this is 9 over 100 over 1 minus 1 over 100. 9 over 100. Let's see, what's the easiest way to simplify that? Probably multiply top and bottom by 100. It's an old trick from algebra to simplify a complex fraction. That'll get you 9 on the top and 100 minus 1 on the bottom. So that's 9 over 99, which is 1/11th. So that's the sum, and it does converge. For this one, same instruction. Now, this one's a little bit harder to deal with the nth partial sum of, because it's not really something you can easily do combinations of the terms with each thing. But if you do a little trick here, you note the common term here is 5 over n. You note the nth term is 5 over n times n plus 1. I'm going to do something. I'm going to split that into two fractions using partial fractions. You'll see why here in a second. So this will be 5 equals a times n plus 1 plus b times n. And I can do any n I want in this context. In this, I really couldn't. N would have to, I couldn't really plug in a -1 in the sequence, but I can here. This is just an equation. So if I let n equal -1, I get negative b equal 5, so b equals -5. If I let n equal 0, then I have a equal 5. Okay. So that tells me then the general term could also be written as 5 over n minus 5 over n plus 1. And that's an interesting case, because that means the first term then, this is 5 over 1 minus 5 over 2. This term is 5 over 2 minus 5 over 3. This term is 5 over 3 minus 5 over 4. Well, if you think about that then, s sub 1 is of course 5 over 1 minus 5 over 2. S sub 2 is 5 over 1 minus 5 over 2 plus 5 over 2 minus 5 over 3. And notice the middle terms cancel each other out, and we just get 5 minus 5 over 3. S sub 3 then would be 5 over 1 minus 5 over 2 plus 5 over 2 minus 5 over 3 plus 5 over 3 minus 5 over 4. And that would just be 5 minus 5 over 4. S sub 4. I'm just going to take this, 5 minus 5 over 4. That's the sum of all these terms. Plus 5 over 4 minus 5 over 5. So this is 5 minus 5 over 5. I think you can probably come up with s sub n at this point. In every case, this 5 has been there. 5 minus 5 over, and you note the number on the bottom is always one more than the index of our partial sum. So this is 5 over n plus 1. So that's the formula for the sequence of partial sums. Then that means we can determine pretty easily if this converges or not. Limit as n goes to infinity of our sequence of partial sums is limit as n goes to infinity of 5 minus 5 over n plus 1. And I mean, you can take your time to see if you can work that out or not, but denominator is going to infinity, so this is 5 minus 0, or 5. This is called a telescoping sum, because the subsequent terms cancel each other out. Really all you see is the end point with each. The only new term you get is really the last term with each subsequent partial sum. Let's look at this one. So this is a geometric series, the problem tells us it is. It may look a little bit odd, but it is indeed a geometric series. So let's see here. Geometric series run k equal 1 up to infinity of a k to the n minus 1, k to the ar to the k minus 1. Now if you re-index a little bit, that's something you can do of if you want this to start from 0 instead of 1 to match up with this, then that would become, let's see, if I want 0 here, it means I need k equals n plus 1. So then I have n plus 1 equals 1. Yeah. So that becomes n equals 0. Top, I mean, if you plug infinity in for k and solve for n, it's still going to be infinity. So infinity. And then this becomes n equal k minus 1. So it's ar to the n. And this then will still be a over 1 minus r if absolute value of r is less than 1. If it's not, it's still divergent. So let's see here. I think we can put it in that form. Note, I do need everything that has the exponent in together, because that's the ratio. So I'm going to pull out that 5, put the negative 1 up there. So negative 1 to the n over 4 to the n times 5. So that's 5 times negative 1 over 4 to the n. This is my common ratio. This is my a. So this should just come out to be a, 5, over 1 minus negative 1/4. That's 5 over... I'm not going to bother multiplying this one. That's just 5/4. So that's going to be 4. Alright. Moving on. Here's another telescoping series. We'll find a formula and see if we can make this work. I think this will be similar to last time. This one's already broken up for us, so if we look at s of 1, it's 3 over 1 minus 3 over 4. S of 2 is 3 over 1 minus 3 over 4 plus 3 over 4 minus 3 over 9. Yeah. So I'll do one more, but I think you can see where this is going. 3 minus 3 over 9. So this one will be 3 minus 3 over 9 plus 3 over 9 minus 3 over 16. So this is S of n is 3 minus 3 over n plus 1 squared. So then take the limit as n goes to infinity. This converges to 3. Here's a neat application of geometric series. It's the last one we're going to do for this video. So if you have an infinite non-repeating decimal, so 234, 234, 234, 234, etc. In college algebra, we know how to convert to an infinite repeating decimal just by division, but you don't really talk about how to convert back. Well, it's a very simple operation, because this we can express as a series. Now this is 0.234, right? And then every time, let's see, there's 3 digits, so move the decimal place 3 digits to the right, so 1/1000th to the n minus 1, and equal 1 to infinity. Yeah, because that one, the first one will be 0.234, which is the first 3. Then times 1/1000th will be 0.000234. Yeah, so 0.234 plus 0.000234 plus 0.00000234. And that'll keep tagging on these 2 3 4s. But this is a geometric series, So we actually know how to set this up as a finite sum, and from that we ought to actually be able to recover the integer version of this, because every infinite repeating decimal is a division of integers. That's something you learn in college algebra. So, using our rule, we know this is equals to a over 1 minus r. In this case, our a is 0.234, or I'm going to write it as a fraction, 234 over 1,000. And then on the bottom, 1 minus, our ratio is 1 over 1,000. So this is 234, multiplied top and bottom by 1,000, over 1,000 minus 1. So that's 234 over 999. And I believe that'll reduce. Let's see here. I believe that is 9 times 26 on the top. So that's 26, and then over 111. And then 111, if it has a factor, it has to be less than 10. 7, I think, goes... No, 7 doesn't go into it. 3 goes into it, but 3 doesn't go into 26. Really, the only thing that goes into 26 is 2 and 13, so I guess those are the only two things I have to check. 2 doesn't go into that, and I don't think 13 goes into that. 13, 130, take off 13, you get 117. No, it's not going into that, so this is the fraction, 26 over 111. So yeah, it's a neat thing. Allows you to finally convert from an infinite repeating decimal back to a division of integers. That's going to be it for this video. Next time, we'll continue looking at series. We'll look at some a very simple divergence theorem for them. For series, we'll look at a set of properties, some corollaries. We'll dig pretty deep into series before we're through much more of the chapter. We'll look at a lot of different convergence tests and different things, but that'll be later. We still have to finish this intro to series. So, see you in the next video. Have a great day.